With that, I'd like to go ahead and introduce today's speakers. Steve Pollack has served as Technical Manager with the Steel Tank Institute and Steel Plate Fabricators Association since 2018. Prior to his current position, he served for 20 years with the Virginia Department of Environmental Quality, most recently as Senior Petroleum Facility Inspector. Steve holds a Bachelor of Science degree in Biology from the Virginia Polytechnic Institute and State University. Kevin Henderson is a consulting storage tank professional providing a broad range of training and regulatory compliance-related services with specialization in cathodic protection. With 28 years of UST experience, he's widely recognized as an expert in the field. Rick Rogers is a NACE cathodic protection specialist that's been working in the cathodic protection industry since 1985 and strictly in the UST cathodic protection industry since 1989. Rick has an associate's degree in corrosion technology. He's personally tested cathodic protection systems on USTs in many different states, including Hawaii and in Canada as well. And our final speaker, Alicia Meadows, is the UST Compliance Coordinator for Virginia Department of Environmental Quality. Alicia has been in the petroleum storage tanks program for 22 years and has had a special interest in cathodic protection systems. Please join me in welcoming our speakers. I know you can't clap, but welcome to our speakers. Very excited to have such a distinguished panel today. I think before we dive in, just have one more slide here. You might have already seen it on the website leading into this, but just a quick overview, and then I'll hand it off to our speakers. Today, we're going to be covering the basics of cathodic protection. We're going to talk a bit about the 60-day monitoring requirement, CP testing reports and data, and Virginia's alternative to UST closure. And with that, my pleasure to hand it off to our first speaker, Steve Pollack.
Hi, Drew. Thank you very much for that introduction. Let me pull this up for you. So I'm just going to hit the high points of some of the basics of corrosion history with these steel tanks and cathodic protection. And just wanted to mention, on top of this, what I've done as a regulator in my last year here at the Steel Tank Institute, I've been accused a few times of turning to the dark side, but I have to just say it's the other side. As a not-for-profit trade association, I work a lot with keeping our member factories complying with our specifications and standards, and also served on committees now with NACE, Underwriters Lab, ASTM. So I still work in a semi-regulatory mode, if that helps people. But let me just get moving on. What we'll cover is some of the basics of degradation and corrosion. I'll just talk about that for a quick second now. Corrosion of these steel tanks and steel products is really just a subset of degradation of materials when they're out in the environment. One of the things I picked up over this last year too, if anybody goes to these conferences, you'll see the word corrosion associated with a lot of topics. And what it really comes down to is you'll see degradation of even fiberglass, and you'll even talk about corrosion of fuel. And what that ends up being is diesel fuel you'll hear pretty often referred to as corrosion, but it's fuel that just doesn't meet spec anymore. So just to kind of watch out for when you're looking for topics when you're at a conference and you see the word corrosion, it may be degradation of other products, it may be degradation of fuel. There's lots of research going on with especially biodiesels and ultra-low sulfur diesel right now. But we'll also talk about a little bit about corrosion control, how that works, how you try to defeat the Galvanic series. I'll talk a little bit about steel tank corrosion protection over the years. Probably most of you have UL 1746 incorporated into your regulations. So I'll talk a little bit about that if you aren't familiar with that. And I will say what's interesting is working with UL, working with ASTM, it's interesting to see how much work goes in before state regulators and federal regulators incorporate those standards into their regulations. A lot of testing, a lot of work goes into making sure the products that we're talking about as regulators are safe and are protective of the environment. I'll mention a couple of high-level notes about test protocols for galvanic and impressed current systems. And I'll touch real quick on our Steel Tank Institute recommendation for adding supplemental anodes. I shared this first picture. This is one that shows up in a few classes. And it tries to show the point where when there's a technician doing a cathodic protection test and taking local readings over top of a tank, you can see that where these numbers are points, and they're actual numbers from actual reference cell locations of where technicians can have taken readings from, and you can see that whatever the technician wants, to a degree, he can make things happen. If they need the tank to fail, you can find a spot like you see in a few of these spots. They're a little low. One spot is. There's also places that pass. If you want to pass a tank, you can certainly find some other galvanized material that can give some readings that aren't quite as accurate for cathodic protection as you'd want. And I'll hit on how to get around that issue in a little bit. Basic corrosion concepts are, if you've ever been in a chemistry or a physics class, you may have seen this scale that shows metals from a passive state that are fairly stable to active metals. And you'll see gold and platinum. Obviously, people are used to seeing that as a stable metal. That's why rings are made out of that. That's why equipment that, in catalytic converters that you need to last for a long time, those metals are stable. Unstable metals that are willing to give up electrons and react are at the top of this scale. And so you'll see magnesium and zinc, and you'll see steel in the middle. So an active metal corrodes easily. So that's a way to take advantage of how this works and add that to cathodic protection and make sure that you're adjusting for linking an anode to a cathode properly. And when it boils down to this is essentially a battery. You create a corrosion cell. So you have one metal that you can see from DC current flow is giving up electrons to a cathode. With a corrosion cell, you have to have certain parameters met. You need to have a pathway between the anode and the cathode. The metals need to be in an electrolyte. In the cases we're talking about mostly, it's either groundwater or it's just moisture in backfill and soil that these tanks are buried in. So this is a pretty easy way to take advantage of adding corrosion control by using an anode and connecting it to another metal object and protecting it by adding current flow. So one of the other issues that we talk about too is steel plate has been worked. It comes from iron ore and you add energy to it. So one of the questions comes up is if a steel tank is completely isolated from the soil, it's coated like a stiff 3 tank might be, what's the concern about corrosion in those instances? One aspect is these steel plates are made up of essentially crystals. I'm sure a metallurgist would get fired up over my description of that, but there may be different spots even on a steel plate and even on a plate as it's worked into a tank that may end up with different values. And it's obviously those are connected, and here's just sort of a puzzle piece description of, you may have a value of 585 millivolts next to 600 millivolts. So you're setting up a corrosion cell between almost like microenvironments. So the potential when people are measuring for cathodic protection is really just an average of all the steel. And so what's going on is sharing of electrons across to protect that plate. So one of the things that we worked with years ago was what everybody knows now as a STIP-3 tank. There are a few components that are required to make up a P3 tank. And that's electrical isolation from the soil, from the backfill. You want to isolate from other steel piping, isolate from copper. So you do that with nylon bushings. I think people have seen that. If you haven't seen that, I can get there'll be some pictures in a little bit of that. External coatings help protect the tank, keep the bare steel tank away from soil. And then the addition of galvanic anodes, which allow a small amount of current to cover the tank, and where there may be spaces where there's a holiday in the coating, or if the coating's been damaged during installation, there's enough current and enough electron flow that can help protect small spaces. Again, you can see there's below the STIP-3 label is where some sacrificial anodes are, and there's just not enough current in those anodes to provide full protection of a bare steel tank. So that's why these tanks are coated. Again, these are just the components to defeat that galvanic scale. And so again, pictures of anodes. Here's a picture of a nylon bushing that has to be installed in the fittings on top of a tank. And I found this I think most people are familiar with Tank Talk. If you haven't subscribed to the Tank Talk newsletter, you can visit the website. I'll provide Drew with a link, and you can get some background information and some archived newsletters. This is an old artwork from when the tanks were shipped with the anodes on, or even it shipped separately, and it was up to the contractors to do the job of adding the anodes to the tank. And as the comment bubble shows, I'll just pull this white thing off so the tank will fit in the hole. That was a problem. I think people are familiar with the other old problem of not taking the protective packaging off the anode so that it can get wet and become activated. So this was an issue for years, and the solution to that was for our member factories to start welding on the anodes directly to the tank. And I just want to give a little bit of, here's some background on some of the initial steps of steel tank corrosion control. In the late 50s, people tried to wrap tanks in plastic bags and tape those up. I'm sure those gentlemen there are following all the OSHA rules, including smoking on site. And I'm sure if this was a Virginia August day and it was 100 degrees and 95% humidity, that must have been a wonderful job to work on that tank. So that actually worked okay. There were some tank removals where tanks that were wrapped up properly came out looking okay. But it was time for the industry to move on and look at better options. And this is one of those tank systems that it's interesting now to come to the Steel Tank Institute and literally talk to the people who wrote the book on steel tanks and corrosion protection. So there was a tank that was developed in 1968 that I had never heard of, and it was one of the first steel tanks with a fiberglass coating, so a first composite tank, so to speak, and it was called Stylife. One of the nice things about developing that tank was it was one of the first times that production specifications for a group of factories was pieced together, and it was the initiation of a quality control program where there's independent inspections going on. This tank worked okay. The standard was only in effect for 5 years. Members had a difficult time creating a tank that actually looked okay. They had a problem with getting all the fiberglass to lay down evenly. So it was an ugly tank. So people ask all the time. I used to ask Lori Granowy this question: when were the first P3 tanks? So the STIP-3 tank was actually patented in 1969. So I'm guessing, I know there's probably a few people listening that may have been born before that, but these tanks were patented probably before most of you were born. And since 1969, there had been coating improvements, anode improvements, and one of the things that was developed was that the Steel Tank Institute had to go through was to get the coatings tested on their own, testing anodes, how they're manufactured, how they're welded on, how they survive, being pulled off or not. And then we have the bushings for that electrical isolation, and Steel Tank Institute developed tests for those bushings to make sure they did their job. One of the other corrosion control options, I sort of referred to that Stylife as one of the first composite type tanks. There was another association that was made up of some other steel tank manufacturers. If you wondered where Act 100 came from, those were people involved with the Association of Composite Tanks. Even though people were making composite tanks, it was 1987 when that association was formed, and in 1988, Steel Tank Institute actually bought the technology and brought in some of the factories that were already making those tanks. Some of them were already our members, so it was sort of a no-brainer. But I just want to give you a quick background on some of that history and some of those questions I used to call about how old is it possible for this tank that's this age to have been built in, X year. So there's been corrosion control for underground tanks for quite a while. Also wanted to hit on, this is what I talked about, UL 1746 that I'm sure is referenced in everybody's codes and regulations. Some of the basics are it is a UL 58 tank. There's three parts, three designs that are included in UL 1746. One is that pre-engineered cathodic protection system. Two is the composite tanks. And three are jacketed tanks. So I wanted to give some of that history too, and to give a little bit of a concept of how UL works. Obviously, the STIP 3 tanks had been patented and designed and improved from 1969. UL 1746 didn't come out till 1989 was the first edition. So the P3 was actually included in the federal regulation back in the 88 regulation, so it was accepted then. But there was enough effort to say we want to use UL, and other people wanted to use UL as an independent standard. You can see similar things, the pre-engineered cathodic protection system that went into the standard. The ideas were already there and worked on, and UL helped to improve on that and build safety standards and testing standards. And that's one of those ways, and one of those things I've learned over this year is these are great code compliance groups, and what they do is they rely on industry and regulators and other people around to piece these codes together. So it's a real cooperative and pretty intensive investment to make these other reference standards an important and worthwhile listing to be in your codes. I pulled out these words components. I thought that was important. UL designs, there's usually a component and then there's a system. So with this pre-engineered cathodic protection systems, the components are the anodes, the bushings, the tank with the coating. Those differences with composite and jacketed tanks come in where really it's just the tank and the coatings, and they have minimums for the coating thickness. I know when I was in Virginia, we debated about whether Act 100 tanks with the optional anodes should have cathodic protection testing done to them. I know there's some other states that said, yeah, if it has anodes, it should be tested. No judgment. You make your own decisions. But I thought this was interesting information. If you are debating about whether you want to insist on that, I just wanted to give you information on some of the testing that's done just to ensure you that these tanks are tested by UL. The components are tested, so they'll have samples of steel and a coating, and fiberglass tank designs. They'll have a sample of fiberglass and similar testing where they age the sample and then test for whether the coating is still flexible. Is the coating compatible with, of course, gasolines, diesels, but they also put it through tests for even salt water. So I know that's been a concern about encroaching coastal water into groundwater. There's been some concerns, but some of these tanks, to meet the UL 58 and UL 1746 standards, the materials have been tested against some liquids that you might find surprising. And of course, they test for environmental performance, corrosion, permeation. That's just testing the components. And then the tougher part is they'll look at a complete tank and do a round of testing on a fully assembled tank. There's impact tests. They'll also take time at that point to test lift lugs and some of the fittings. If it's a tank with interstitial space, which obviously they all have to have now, the initial design for a new tank, the interstitial space has to be tested and be found that the design is sound. And they'll do holiday testing to make sure that, if 100 mil is what somebody's looking for in the UL standard, that's actually adequate. So just to let people know, there's a ton of testing. It takes years to do, and it's actually very expensive. UL is actually a for-profit company, and it's an expensive undertaking to make sure that if you come up with a new tank design and you want it UL approved, there's a lot that goes into it, which is a good thing. So just want to hit on the broad spectrum of galvanic system testing. Again, voltmeters are important, good test leads, a good reference cell, and a really solid connection to the steel of the tank are important components of a good galvanic test. You'll see here I do have a drawing where there's a 30-foot space between the reference cell and the tank. We'll touch on that in a little bit. Pass-fail criteria for galvanic systems. Here's some testers and trainers out instructing. But pass, if people aren't familiar with it, is the negative 850 millivolt or more negative for on readings for P3 tanks. And what we've looked at now, partly thanks to Kevin Henderson's research, is from our new testing standard, we require one local over top of the tank and 2 remote readings. What those 2 remote readings do is show that you've achieved true remote. Another way to pass is if you've had field installed sacrificial anodes, is for flex connects. I'm not going to get too deep into that, but there's an instant off aspect that you want to look at. So true remote is one of those important concepts. True remote gives an average of the whole tank, and that's why at this point we're more in line with the idea that one center local reference cell location, and then proving that you've met true remote and taking those readings is better than taking 3 readings over top of the tank. Keep moving the reference cell away from the tank until you hit a 10 millivolt difference. That's you can see how these in this top of the slide, those numbers are changing, and then once they start to lock in, that true remote is what gives you the idea that you're away from, if you see concepts of shielding and raised earth, you've gotten away from that interference, and you're actually reading an average for that tank. In press current system testing, very similar. Test leads, good contact with the tank, a good voltmeter, but still within press current system testing, you're looking at this point, just 3 reference cell readings over top of the tank. We're not looking at remote. Remote doesn't work from press current systems. a few of the terms you're going to come across, native potentials. Those are only when a tank has not had cathodic protection applied to it. You might see people try to use the 100 millivolt shift to pass a tank, and they're going to say they're adjusting that to native potential. But if the impressed current system has been installed for 10, 20, 30 years, that's no longer true. Even if you have the original design requirements, what we really should be looking for is the depolarized potential to make that calculation. The other term you might hear is about static potential, depolarized potential. It's after the cathodic protection has been interrupted and the structure is depolarized completely, or long enough for you to get a reading. It's usually used for that 100 millivolt shift and to meet that requirement. Polarized potential is that second reading, if you hear that, and the instant off potential, and that gives you a reflection of the impressed current system is off. You've eliminated current flow through the ground, and that eliminates what you'll see a term called IR drop. Really, that's just interference from the current. But if you take that reading as quickly as you can, once that system is turned off, that's still the potential of the tank before it starts to degrade. And that's where you start working with, did you meet the negative 850? So here's pass-fail criteria. Here's people checking out a system and a rectifier and taking measurements. So here again, negative 850 millivolts DC or more negative for instant off, or if you take 100 millivolt shift reading for those 3 local stations. A fail is you can't meet either of those, the 850 instant off or the 100 millivolt shift. The other way to fail a tank too is with impressed current, is if the continuity of the structures that you intend to protect can't be established. That's one of those important concepts with impressed current systems. The other concept, this applies to impressed current and galvanic. There's no testing through asphalt or concrete. You'll have to drill a hole to get in touch with soil or backfill. Continuity testing. It can be used for troubleshooting for galvanic systems. And the concept here is, like I showed you, the coatings and the isolation bushing. Galvanic systems have to be isolated from metallic structures and obviously the ground. But here we're doing continuity testing between the tank bottom and piping and any other structures. And so isolation for galvanic systems is the key. Impressed current systems, it's the opposite. Those structures that you're trying to protect, they need to be bonded together. I just want to emphasize that continuity is critical for those impressed current systems. And it's important that when you're reading reports that you see that the technicians have included that test in the full report. One of the things we do have is if a STIP 3 tank starts to fail, starts to dip below that negative 850, we do have a standard for adding supplemental anodes. It's a really conservative recommended practice. It does allow experienced people in the tank world to avoid using a cathodic protection expert. But again, it's very conservative. You have to do a current requirement test. You should probably be doing a soil resistivity test. And the limit to bring a tank back to that 850 criteria, you can only need 30 milliamps. If it needs more than 30 milliamps to bring a system back to 850, then you need to contact a cathodic protection expert. So we do have in the back of that standard a form that the technicians should be using to state how they've calculated the current requirement and how they've calculated how many anodes were needed to bring the system back up to compliance. One of those things that regulators should be doing is if you're not asking for some other calculations on some other form, you can always refer them back to this form and say, I need to see this this form and this checklist from the back of the RP 972 recommended practice needs to be completed and filled out so that you can file that with the records for the tank. So I just want to thank you for your time. I appreciate it. One of the other ways, rather than just these webinars, is invest in some training, whether it's you can work in some NACE training, whether you can, there's an Appalachian short course in West Virginia that's good. I think people are familiar, obviously, Steel Tank Institute has cathodic protection tester training, and we really do like working with regulators and like having classes with regulators to make sure everybody knows what to look for and are not confused when technicians start turning in reports. So I appreciate your time. Thank you very much.
All right. Thank you so much, Steve. A very comprehensive look at things to get us started here. And I did, looks like I've got a good question from the audience here. It's kind of a longer one. And I think what I'll be doing if you were on Tuesday, I'll see for now if I can, I'm actually going to table this question. I'm going to save it onto a PowerPoint and pull it up at the end, because I think it's one that we definitely want to hear Steve comment on, and maybe one that we could hear from the panel on as well. And I'm just kind of keeping an eye on the time here. I know I got us started a little later than I'd planned as folks logged on. So I'm going to table this really great question here. Thanks for sending that. And we'll go right ahead here, keep things going. Still have a lot to cover today. So it is my pleasure to go ahead and hand it off to our next speaker, Kevin Henderson.
All right. Thank you, Drew. Always appreciate the opportunity to share a little knowledge and talk to everybody today about CP, my very favorite subject of all time. One of the things that I want to try to cover a little bit today is spend a few minutes on and help people understand this thing about monitoring of impressed current systems. Everybody's familiar with these so-called 60-day check. Been around in the federal rule, of course, forever, and seems like it's always been just kind of ignored. Not a lot of attention paid to it. Nobody, and I think it probably has more to do with people just didn't really understand what it was really intended to do. So I will start by saying that, well, it was not ever intended to verify that the power is on. That was not the purpose of it. Now, that may be what really happens in most cases, because we know rectifiers get turned off all the time for various reasons, and so the looking at it periodically does at least accomplish that it is, in fact, turned on. But that really is not the purpose of it at all. And so we just need to understand, and I'm going to try to help us understand by answering about 4 questions here today about how am I supposed to go about doing this monitoring, and most importantly, what is it telling us? What is monitoring the rectifier telling us? In other words, what am I looking for? And then, of course, the whole gist of it is what happens as a result of this monitoring. What actions do I need to take, if any, and when? And then lastly, of course, yes, I'm a former regulator, so I'm always mindful of how can I make things better. That's what we're here for, right? So when I talk about monitoring these systems again, we have to understand a little bit of the background about where this came from and how it came about, because waiting 3 years to do a test on an impressed current system, quite honestly, is just a horrible concept. That's a terrible idea. Way too many things can happen within that 3-year period. It's just really, really far too long to go on testing impressed current systems. On a galvanic system, that's probably okay. Nothing wrong with that, but definitely not on an impressed current system. So how did this happen? How did we wind up with this 3-year testing requirement in the federal rule? And I suspect what happened was is they compromised, as they do very frequently, and understood that 3 years was too long, so they put in this monitoring requirement, 60-day monitoring requirement. So the monitoring requirement is intended to ensure that the system is operating correctly during that 3-year testing interval, because, like I said a couple of times already, 3 years is just way too long to go. It's kind of odd that they gave it 60 days. Most everything is 30 days, so that's what we typically tell people. That's what I do. Anyone that I deal with, and always done that, is just do it every 30 days, even though the rule actually is 60 days. It's much easier to keep up with, much simpler to do 30 days. And, the deal again here, of course, is we're talking about impressed current, so we're looking at the oldest tanks in our universe, if you will. And so what that means is, of course, they are the ones most likely to fail, the most vulnerable ones. They're the ones we should be paying the most attention to. This monitoring, again, should not just be an offhand, oh, by the way type thing. This really is the crux of the issue relative to impressed current systems, is monitoring these systems properly and correctly. Almost every impressed current system that we have was put in, to meet the deadline. I was around during the deadline. It was the heyday of the program, if you will, lots of excitement. But this all ended in December of 1998. Now, all these systems are now 20-plus years old, and the tanks that they are protecting are anywhere from 25 to 50 years old. Yes, we do have some very old tanks still in the ground that have impressed current on them. So these are obviously the most vulnerable tanks that we were talking about trying to protect, are these impressed current systems. Skipping around here. Yep. So we're going to verify that our gauges are accurate. One of the ways that we do that, to get on the right slide here. Okay, I apologize for my navigation error, but they're not going away anytime soon. These impressed current systems are going to be around for a very long time. It's not like people can afford to put in brand new tanks. That's a very expensive proposition today. So where these impressed current systems still are at some very marginal locations, if you will, and so I just don't see them going away anytime soon. So we just got to deal with this. We're going to have to deal with this for a long time to come. And again, this monitoring thing is what this is about. So we're looking at the gauges basically on the rectifiers, if you will. The volts, the amps, and the hours. This is the typical thing everybody looks at. And assuming that the gauges are correct is one thing. So whenever you do this, particularly as a regulator, I always like to get out my multimeter and check the accuracy of the gauges. This is a pretty simple thing to do. Measuring the voltage is, of course, a very straightforward thing. Just connect it up to the positive and negative and see what's on the meter. Checking the amperage output, which is what really matters, of course, is a little bit different. We'd use these things we call a shunt. So you've got to figure out and learn how to measure the voltage across this shunt, go through a little simple calculation to determine what the amperage is. It's easier said than done. So we don't always get this right, but if you don't want to fool with that. If you don't, there's always these clamp-on meters that we have today. So we're lucky enough today to have these clamp-on meters, which we just put them around the wire, and it will read the amperage directly, so it's not that big a deal anymore. Looking at the typical rectifier log that people keep, the so-called 60-day check, if you will, this is what you typically would see, something similar to this. Date inspected, is a rectifier turned on or not? That's what everybody believes the whole purpose is, of course. Then where are the tap settings at? What's the voltage in the amps, the hour meter? Who did it? And so there is something missing from this form. It's always kind of puzzled me on how this all came about. But what's missing is no one understands and pays attention to the amperage. And the amperage is what this is really about. So there's no specification on this type of log or form that would give the owner who's doing this monitoring or the service guy doing this monitoring a clue as to how many amps they should be looking for. So it's all well and good to record this data, but if you do not know what the purpose is or what the action level is, then it really doesn't serve any purpose. This is a different version of a form, a simplified version, but what I do like about this form is it at least attempted to give you what the recommended amp range was, even though they didn't specify what that range was. And this is very typical what you see out in the real world. Somebody's looked at this thing maybe once a year, maybe every 2 years. At least somebody has looked at it and recorded the voltage in the amps. And you see it's gone down to 0.3 amps on the last check that was made. It went from 3.2 to 0.3. There's been a big change, obviously. Something drastic has happened, but no one has paid any attention to it again. In fact, they marked, yes, the system is still running properly because why? Well, the power's on. That's the only thing anybody's ever understood about it. So, told you already, I think you've got the idea that the amps are what matter. But everybody always wants to know, well, how many amps are required? How do I know how many amps do I need? And, of course, the standard answer is there's just way too many factors that go into determining what the amp should be, but it should be specified by the guy who designed the system. The engineer who designed the system should tell you how many amps are needed. We can make a very general rule of thumb that we like to talk about, and it is a very broad rule of thumb that you need about 1 amp per 10,000-gallon bare steel tank. So if it's an old bare steel tank, a pre-88 tank, if you will, you would expect to see somewhere in the neighborhood of 1 amp per tank. Obviously a coated tank like a P3 tank or an Acrid 100 that's been retrofitted with infrared current will require very little current because of the nice coating on the tank. So very rarely do we know what the specified amps are by the engineer. We almost never have that kind of information. But what we can do is we can look at the last passing test that was conducted, and we can look and see how many amps were in the system when that system was last passed. And then that gives us an idea of what this, quote, normal operating range is. The amps will vary a little bit depending on the weather, how wet or dry it is, but we're looking for it to be fairly consistent in a fairly narrow range. So we see this, look at the gauges. Oh, okay, I've got 5 amps, everything's cool, no problem. Then we look at a system like this where obviously there's no volts and no amps. Both are on 0 or close to 0. This is not hard to figure out. There's something drastically wrong here. Probably, as we all are very familiar with, the power is probably not even on to the rectifier. That's what this typically means, is no one or somebody's thrown the breaker. This is fairly common these days to see this, and this kind of puzzles people, I guess, for various reasons. When they see the voltage, got plenty of voltage, what we would call normal voltage, or maybe even be maxed out on the voltage, but 0 amps. And so this is what we're actually trying to accomplish by doing 30-day monitoring, is when we see the amp fall below where they should be, it is time for us to respond. You don't get to wait 3 years. And so the central message is, I don't really care what the voltage is. The voltage can be almost anything as long as it's not 0. But when you see that amp meter go to 0, it's very clear, then I have 0 CP. So if we look at a kind of an idealized rectifier log, we can get some really good information off of these when they're done correctly. So this is a form that's been designed by me that's created to help people understand what it is I'm trying to do here and when do I have to take action. So if we look at the way this is going on, the voltage stays more or less the same because almost every rectifier that we have in our systems are what we call constant voltage rectifiers. And what that means is, unless someone has physically changed the settings on the rectifier, that the voltage will not change. It will stay the same, assuming that the power is on and nothing has happened to the rectifier itself, then the voltage will stay very close to the same. And so what we're trying to monitor and pay attention to are the amps. And you see that the amps do vary a little bit over time. This is a once every 30-day check, if you will, and you can see that the amps go from 4.2 down to 3.8. And then we see that on July, we got a sudden change to zero amps. Although the voltage stays the same, the amps go to zero. And what this almost always means is somebody has cut the wires underground. Some kind of construction work going on at the site, or something happened, and almost anything can happen. Lots of things that happen that cause this to occur. Or I'll suddenly go to zero on the amps, and so this is a very clear indicator of a big-time failure. Somebody has cut the wires, all of the wires probably. But if you look at the top of the form, you see that it says that the minimum design amperage, there's an entire section devoted to this, and it specifies very clearly that the minimum output needed to provide adequate CP is 3.5 amps. Where did that number come from? And again, that's from the design guy, or if you do not have that, pretty simple to calculate what you should have, and we just take 20% of what was present at the last passing test. So in this case, it was 4.3 amps was the last passing test, and that was from September of 17. So we can do some math there, where I'll show you in just a second, and come up with that number ourselves. See this also from time to time. This is not unusual. This is a different example of a rectifier log, and what it's telling us when we see the data, again, the voltage stays the same, constant voltage rectifier, nobody's changed it. And what happens is, over time, you see the amperage declining, and it is a significant decline. It's not just a normal variation that we would expect. It is a significant decline. And so we're starting out around 4.2, 4.1 amps. Then come July, we see we're down to 3.4 amps. The guy doesn't do anything because he probably doesn't know he needs to do anything. And we go further on time, and see we go down to 3 amps and then 2.4 finally. And so what this is telling us, if I have multiple anodes in this system, more than likely, most systems have 6 to 8 anodes. And this is a system where the design has individual anode lead wires. And so what you're seeing is the anodes failing one by one. So probably with all of the anodes operating, we were around 4 amps. When one of them failed, we went down to 3.4. We had another one fail. We went down to 3.0. We had another one fail, and that 2.4. So we get this stair-stepping down, if you will, because we're losing anodes. They're dropping out in the system. And so again, this owner, regulator, needs to recognize that this is what is happening and understand that there comes a point in time where I'm going to have to take action. I do not get to wait 3 years to figure this out again. And so there is the generally accepted rule of thumb, again, is 20% of the last passing test. So find the last passing test someone did, look at how many amps were present, and do the calculations and figure out what was 20% of that. In this little simple example, maybe I had 5 amps at the last passing test. 20% of that is 1 amp, so 5 minus 1 is 4 amps. What that means is, if my amperage falls below 4 during the course of my monitoring, then it is time for me to take action. So this is the way the rectifier log should look again. You need something that looks like this so that people can understand what it is I'm trying to accomplish and when do I need to take action again. So here in this simple example again, I had 4.5 amps at the last passing test. The minimum specified by the engineer in this example is 3.5 amps. And so we're emphasizing the amps column, trying to match that and put it in their mind that this is what I'm actually looking at, is the amps, and I got to have 3.5 amps. So this is a different version of that form, actually, that's designed to emphasize the amperage aspect of this even more. This version of my form will cover 3 years. So that fits between the 3-year testing interval. You don't really need to know all this other stuff, but the only thing that you really need to know and must know is what are the amps in this system. And so this is what this form is designed to do, is very clearly make that obvious to someone, as obvious as can be. And so how can we make it better? I would encourage everyone to adopt these forms or a version of this form or something similar to it to help people understand that this is the AMPS is what this is all about. This is always an education thing. There's a lot of education involved in regulating underground storage tanks. We're all very familiar with that. New owners every day, people who just don't really maybe have quite the education that other people have. And so we have to make a lot of effort to educate people. And I have yet to see anybody's Class A, B, or C operator training really delve into this issue. There are plenty of impressed current systems still out there. The operator training really needs to address this issue because these are our most vulnerable tanks. These are the ones we should be paying the most attention to, and we just don't seem to really be getting that message across. And, of course, we can train, we can require, but until somebody gets spanked for not doing what they're supposed to do, I think we all realize, that enforcement is always a part of it. No one likes to talk about it and do it, but people are going to have to understand how important this is. I think it's just something that's been overlooked for far too long. So with that, I will shut up. I'm going to offer that if you like this form, I'll be happy to share this form with you or any forms that I have. Audit protection testing and monitoring. I've got lots of forms. I'll be happy to do that. Just shoot me an email and let me know. Thank you very much.
All right. Thank you very much, Kevin. And speaking of the forms, I did get, one of the comments out there was just an appreciation for, showing some of the what the viewer called, real world examples. I know that's something we had kind of talked about in planning this is really showing what it looks like. That was much appreciated. So great job with that. What I'm going to do, I'm going to invite the audience for Kevin to go ahead and send me a question or two if you got one. And then I'd mentioned I tabled one earlier when Steve presented. So I think we're kind of getting back on track here with time. So I apologize a little bit to the panel here for jumping around. But I'm going to just pull up a couple of questions here real quick that we got right in the transition between Steve and Kevin. And, we'll discuss those questions here for a minute. And then, again, I'll invite the audience to send questions, for either Steve or Kevin right now in the chat bar while I upload this. Just give me 1 second. I'm going to pull this up. So, Steve, I think this came in at the tail end of your introductory presentation there. Let me go ahead and pull the controls back just to make sure you all are seeing this. All right. Do you all see that question?
Yes.
Okay. So I'll read it. I know it's on the screen, but just so folks can see. So the question, please comment on any USTs installed during the UST interim prohibition and the law allowing an exemption from the requirement of corrosion protection if an US system is located at a site having soil resistivity measured at 12,000 ohms per centimeter or greater. A pretty specific question there, but I wonder if maybe you could try to field that one, Steve, and feel free to follow up after Steve if you want, Kevin.
Yeah, I mean, I think this was, days of, pre-88. And I was trying to pull up an old preamble to see how the preamble took care of it. But, I think it was, a request and, how these things work was that amount of resistance, there had been, a corrosion expert or a PE, if I'm remembering right, could sign off on that. I was hunting through the attendees list to see if Tim Smith or one of those folks, but Kevin and Rick might remember too. I did see Russ Ellison's name on there. He may actually be able to comment to that too if Kevin or Rick don't know that.
Yeah, Steve, this is Kevin. Yeah, we didn't have anybody actually try that. No, I don't think anybody understood what that meant. We're a bunch of stupid rednecks down here in Mississippi just didn't understand what it meant. Nobody even tried to do that.
I apologize for not being able to pull the preamble out to see what the EPA discussion was, or if I was looking to see if Tim Smith or anybody from ALST were on. That
no worries. I think maybe you know, when this comes up, you know, if you know, we can always continue the conversation offline. I can reach out to those folks, and if there is something that we can you know, include on the archive with this presentation, I'm happy to do that. So we'll circle back on that. Thanks so much for the questions in the audience there. And I did get maybe one that's a little more softball-ish. Can we assume any tank installed prior to 1987 is not a composite tank?
I would not assume that. I mean, that was just when an association was formed to document those. You know, again, that in a way, that Stylife tank back in 1968, that was a composite tank. That was a steel tank with a fiberglass, you know, coating applied directly to it. So that, in a way, was a composite tank. That reference was just a reference to the association, and then to the trademark technology name for Act 100. But we can delve into that a little further too. I know that's one of those questions that pops up, and that's actually one of the things I want to go through with Wayne Geyer, who's been here for over 30 years and knows a lot of the history. I just want to get that posted on our, sort of a brief history posted on our website.
Great. Well, thank you.
This is Kevin again. I can tell you from direct experience that is not true. There were a couple of manufacturers here in the South who were building composite tanks well before 1987. They just weren't called that. They didn't know what to call them. In fact, there's quite a few of them around in South Mississippi and in the Baton Rouge, New Orleans, Louisiana area, because that's where they were being made at by a company called Ream Manufacturing, like the water heater company. Yeah, they made a bunch of these tanks.
All right, well, there you go. So don't make the assumption, especially down there. And then I think this question that just came in, so I'm going to do one more. I think this one's for you here, Kevin, in response to your presentation. So the question is, and I don't have it to upload, I'll just read it aloud. The question: could a significant change in voltage readings indicate an attempt to hide a fluctuation or declining trend in amperage?
Yeah, that's of course a great question. And assuming that it is a constant voltage rectifier, if people will start cranking on them, right? Yeah, they'll try to crank on them to keep the amps going. And so what he's talking about is the example I showed where the anodes are dropping out one at a time. You know, the typical response is to start increasing the voltage to try to keep the amps within the specified range or where they should be. And sometimes that works, sometimes it doesn't. Sometimes it can be very detrimental. It will cause the rapid depletion of the remaining anodes is what typically happens, or your current distribution is just not good enough anymore to pass everywhere. So, you know, this is not a perfect system by any means. With these constant voltage rectifiers, though, as long as you see the voltage remaining the same, the monitoring is very significant. But when someone starts cranking on them or changing the voltage, you really need to start testing again to know whether you can still pass the system or not legitimately, and so it becomes, you know, a problem for sure. People cranking on rectifiers, not realizing, not understanding exactly why or what they're doing again. And I might mention just in passing, I've got just a minute here, there are some constant amperage rectifiers out there, just the opposite of the constant voltage. The constant amperage rectifier is designed to change the voltage on its own without any manual input. It will change the voltage in an attempt to maintain the design amps. And so there are some of these systems around, not many. Usually if you see a rectifier made by a company called Technology, they put in quite a few of these constant amperage rectifiers, so it is possible that you will run across them. So be aware that they are out there. The vast majority will be these constant voltage rectifiers.
All right. Thank you so much, Kevin and Steve, kind of fielding those questions back and forth there. Appreciate you being flexible as they come in. That's how this goes sometimes. So great start, 2 good presentations, a handful of good questions, and of course responses as well. So I saw another one came in. I'm going to table it for now. And we're going to go ahead and hand it off to today's third speaker, Mr. Rick Rogers. And Rick, take it away when you are ready.
Hello, everyone. Thanks for participating today. So I was asked to address the situation. I see many test reports come in to me for review. People ask me to look at, people ask me to do repairs on systems. And I see these reports, and a lot of them I see they're either incomplete, they're not accurate, or the tester doesn't really understand the proper text. So my presentation today is going to be about these reports. Is the test complete? And you guys as regulators should have at least a little bit of knowledge of what you're looking at when you look at these reports. I know I've had it told to me, you know, a lot of people, including tank owners, they just want to see that pass box checked. And I think as regulators, we, you know, really should be doing a little more than that. So hopefully going through my presentation here, I'll educate a little bit more on how to look at a test to make sure that the test is being done properly and, you know, that it's a legitimate test. I've honestly seen test reports that were totally falsified. I could tell the reading stood out to me, but a lot of people it wouldn't. So hopefully you guys will learn a little more about that today. I'm going to start off by saying about sacrificial anode and impressed current systems. Sacrificial anode systems are limited in what they can do. The sacrificial anodes produce minimal current, typically anywhere from 2 milliamps to 80 milliamps per anode, depending on the anode material, the size of the anode, and what it's installed in. A sacrificial anode, its life is strictly dependent on how much current it produces. Impressed current systems is totally different. We have a different anode material, which is more like a ceramic material. These anodes can produce high amounts of current and have long lives. A lot of anode manufacturers have designed their anodes to produce up to 2 amps with a 20-year life. What we're seeing out there real world is that you know, you're getting maybe 16 years if you push an anode at 2 amps. But the idea is that the more amperage that you push an impressed current anode at, the shorter that life will be of that anode. The thing about impressed current systems, they can be designed to protect any size structure. So they're very universal and can fit most situations. So looking at a sacrificial anode test report, we want to see some minimum things there. And it's obvious, you know, typically in a CP test report, we want to see owner information, site information. We'd like to see the information about the tester, who did the test, what company they're with, if they have some certification, you know, what that certification is, and obviously a signature and a date by the tester. We definitely want to know when the test was done, and then also we want to see, you know, their conclusion. A lot of test forms, you know, will have pass-fail sections to check or mark. Some state forms I've seen also have inconclusive sections on sacrificial tests. And what we teach in this STI class that we teach, that inconclusive by a tester is really a fail. The inconclusive only gives the tester an option to pass it off to a corrosion expert, and they can evaluate it and determine if the system is really passing or failing. And then, of course, you want to have the next date of the test stated in that report. The next sections we're looking at, usually in sacrificial anodes, we want to see you know, information about the systems, the tanks, sizes of tanks, construction material, and certainly if you have an STI P3 tank, it is a steel tank, but we would like it, you know, to see it stated as STI P3 as the construction material. The one big thing on these reports that I just get so frustrated with are these flex connectors. I think we all do. Even you guys as regulators probably do. But we need to know if they're there. We need to know if they're not touching an electrolyte, and that's a key word, electrolyte, or if they are they cathodically protected? And of course, we use the word electrolyte because it came about a year ago in a state that I'm involved with, where there was a statement made if they're touching soil, and that became an issue because a lot of these flex connectors in containment sumps may be sitting in water. They can't keep the water out. So, that became an issue, and I think it got clarified, but we use the word electrolyte, anything that's conductive, soil, water, moisture. The next thing we want to see the continuity test section on a test report. And we like to see those readings stated, at least I do as an expert, because if someone ever sends me a report to review, to look at, to figure out a repair, those continuity readings provide useful data. And if that data's not there, sometimes I can't make repair recommendations or things like that would be appropriate. So we like to see that continuity test data and the actual readings stated there. You're going to have your structure soil potential readings in this report. With a sacrificial system, and it's changed over the years, but again, I follow typically the STI standard methods and the NEI standard methods. And right now we're at a point where we're looking at local reference cell placement readings and remote reference cell placement readings on sacrificial systems. STI's new test standard gets even more specific and states 1 local reading and 2 remote readings. There's a reason for the 2 remote readings. It's to establish true remote Earth. It's a very useful tool and helping evaluate the system and also doing it correctly. We're not going to go into that and why it's done, but it's a procedure and certainly can be discussed or read about in some documents. The last thing is a site drawing. You always need a site drawing. You need to see the layout of the UST system. You need to know the tanks that were tested, if any flexes under dispensers, and you need to know exactly where the reference cell reading came from. If I see a reference cell reading in a form, I need to know where that reading was taken to evaluate what that reading is telling me. If I don't have a location where that reading was taken, it means nothing. So I'm going to give a few examples here of sections in a report that you should see. A sacrificial anode, the tank and piping information, it's pretty obvious. We've got a regular unleaded tank, 10,000 gallon. We specified STI P3. Our construction of piping material was listed as non-metallic. As far as a corrosion person, I don't care if it says FRP or if it says flex piping or plastic. To me, it's non-metallic. So it can be stated either way, doesn't matter. In our example, we show there are flex connectors present at the site, and in his comments below, this tester stated flex connectors are either booted or in a containment sump. Now, also being in a containment sump, it becomes a question, is that a dry containment sump or a wet containment sump? So, that would be some useful information. If that containment sump held water often, it should be protected and probably, is required to be protected now according to clarified regulations based on this state that we ran through this issue about a year ago. Here's the next example of the continuity test data in a sacrificial system. We have structure A. We took a remote potential reading on that tank, the regular tank. We had a 961. We took a remote potential reading on the regular tank fill riser, and we had 572. The criteria is determined by millivolt difference, and I won't go into the criteria. It's out there. A lot of people know it. You can easily look it up. But here we have 389 millivolts difference between our tank bottom reading and our fill pipe reading. That's obviously isolated. If it was the same structure, it should read pretty much the same reading. So by reading different potential measurements, it's definitely isolated. That's just the continuity test data you'll typically see with a sacrificial system. this is our potential measurements on the tank, and this form used is currently under STI, Steel Tank Institute's testing guidelines, where we take one local reading, preferably over the middle of the tank, and 2 remote readings. So you'll see unleaded tank bottom is our contact point, the soil in the ATG riser. We had a negative 883 millivolt potential. The 2 remotes for that tank are 959 and 961. All 3 of those are above the negative 850 millivolt potential reading, so that tank passes. You see in my statements below, if any reading on any structure in a sacrificial system reads a negative 849 millivolts or more positive, then that's a fail or an inconclusive. You have to have all the readings. Also, and I like to discuss this on these sacrificial systems, we're typically talking about STI P3 tanks. If you look, the remote readings on the 3 tanks here, we have unleaded, premium, and actually the 3rd tank is not a tank, it's a flex connector at an STP pit. But if you look at the remote readings, they're all different. They're all different by at least 30 millivolts or more, just about. That indicates all of those structures are isolated from each other. So the regular tank, in a sense, it has its own cathodic protection system. The premium tank has its own cathodic protection system. The regular flex connector at the STP pit has its own CP system. So when you're looking at these sacrificial tests, a lot of times you're looking at multiple CP systems. So they have to be dealt with individually and separately sometimes. I do know that there are companies out there when they repair failed STI P3 tanks, they'll bond all the tanks together. And, you know, that's not necessarily a bad thing. It just now means that if you had 3 STI P3 tanks and you bonded them all together, well, now they're all tested really as one structure. So if you had one failing reading over one tank, all 3 tanks fail because they're all tied together. Also, I had it brought to my attention, they've seen potential readings in some of these test reports where they see potential readings, you know, negative 200 millivolts or something around 1900 millivolts. In a sacrificial system, you should never see readings like that. If you do, that's indicating that the test was inaccurate. They had a problem with their lead, their meter, their reference cell, or something like that. Or there could be a severe problem with the tank, a stray current problem, something, which I'm not going to get into that today. But that's a sacrificial local potential test report that looks standard, what you would expect to see and want to see. Also, if you'll notice up there, about midways of the example, it says location of remote reference cell 1. It states where that was, in soil behind tank field. Location of remote reference cell 2. 10 feet from location 1. So you need that description. You need to know where those reference cells are, like I said, and you also need to show those on a drawing. Here's an example of the site drawing. You see that this example, our reference cell remote cells are 60 feet away from the tank. We show location R1 and location R2. That's what you should see in a good sacrificial anode test drawing. You'll also see the X's marked over the top of the tank. In this example, they actually took a local reading on the tank in the ATG, and there was a flex connector at the STP that was being cathodically protected. So they took a reading there. So moving on to inverse current, and first I want to stop and say that this is just touching the surface on these things. There are many, many details that could go in, and I actually told Drew that I just had to stop. I caught myself going on, and I had to stop at some point. So this is actually the same information from the sacrificial form. It's pretty standard. They should be on all of them, whether it's sacrificial or impress current, this information here. Typically in a state CP test form, the second page of an impress current system is going to be significantly different. We're also going to have the rectifier information. That information should be there. Rectifier manufacturer, serial number, model number, the rated DC outputs. we don't really care about the AC. There should always be the tap settings, what the rectifier was set on when the test was done. That's important information because if that ever changes, the tap settings, that changes the system, and that could really have some effects on the system, how it performs. And then certainly you're required to read the meters in there. Also, in an Empress current system, I've over many, many years gotten a lot of these reports where I look at the rectifier voltage and amperage outputs, and I can tell that they just read the meters in the rectifier. They didn't actually measure the outputs. And as testers, and we teach our guys this, that they should measure the actual outputs, not just trust those meters, because we all know, and you guys as regulators know, those meters don't always work. So they need to measure it, and that documentation should be there. Ideally, on an Empress current system test report, I would see the indicated gauge readings, the amp and voltage meter readings, but then I would also see the actual measured voltage and output in that report. Again, that's important because those gauges aren't always correct. And as Kevin mentioned in his section earlier, you'd like to see the design amperage output of a system. As a corrosion expert, they should design an operating range of where this system should operate between 2.5 amps to 3.4 amps. That's not there in a lot of these tests and things we see today. What you do then want to see is what was the amperage output of the system during the last passing test. That helps a lot. And as Kevin mentioned, that's going to help us to determine whether the system 3 years later is still operating properly. Also, if there's an anode junction box in a system, the individual anode outputs in a system, especially if an Empress current system fails, those individual anode outputs should be measured and included in a test report. As an expert, I get reports, again, to look at, and many times I don't see any individual anode output readings in that report, but when a tester is sent to the site to evaluate it, we find there is one and it's measured and we find half of the anodes are dead, and that's why the system's no longer passing. So the individual anode outputs is very, very useful information in evaluating the system. And then finally, an Empress current system in the third page, again, we want to see that continuity test data. And also, as Kevin mentioned, it was Steve that mentioned, in Empress current systems, it is extremely important on continuity test data for Empress current systems. We have to see that test data. It has got to be in that report. If you have a structure that's isolated that was intended to be protected that becomes isolated, you can have some severe problems occur, including creating a hole in that tank with the Empress current system. That's what we call stray current. Again, I won't get into that. Nowadays, we see this continuity test done on Empress current systems called point-to-point. It's a somewhat new type of test method that was brought to me years ago. I'll give him credit, Kevin did, that we do nowadays on Empress current. And according to the NEI standard TM0101, which was written in 2012, the rectifier must be off and the negative wire should be disconnected when doing continuity testing on Empress current systems. So really, in a sense, it's almost impossible to do a point-to-point or a fixed cell moving ground test on an Empress current system because the polarized potentials of the structures are changing when you turn that rectifier off. So again, point-to-point method is really good and useful on Empress current systems. You're going to have your local readings in an Empress current system. We want to see the connection, where it was made, location of the reference cell, and again, that's extremely important, must be shown on the drawing. But something we see out there today, the on reading in an Empress current system means nothing. The tester will never use that on reading. The instant off or the polarized potential reading is used to determine pass or fail, and an ending potential reading, static or depolarized reading, is used to determine to meet 100 millivolt polarization if you need to. So again, you guys as regulators understand an impressed current system, the on reading is there, but it's never used for any purpose by a tester whatsoever. Information it does provide is to a corrosion expert when they're evaluating the system. That on reading tells us a lot of things. Tells us about soil resistivities. It tells us about areas of current where we have significant current, too much current, not enough current. The on reading is useful information, but not to pass or fail a system. In an impressed current system, there is no inconclusive. It is a pass or a fail. It's just all there is to it. And then lastly, again, a site drawing. And in the site drawing, it's the idea to show the rectifier location, anode junction box location, and also if any, as a tester, you like to see that they document, they see anodes, you can tell where anodes are, a lot of times patches in the pavement, the saw cuts in the pavement where the cables are run. I try to instruct all the technicians I teach, when you're making a site drawing, if you can see that, show it on a drawing. It just helps so much when you're evaluating a system's performance. So the tank and piping information in an impressed current system, same as before. We have the capacity, the product. Now our tank material is steel, not STIP3, although there are STIP3 tanks that are tied into impressed current systems. If they are, you should document them as STIP3 tanks. In my example here, we have galvanized steel piping, no flex connectors. So as Kevin mentioned as well, if you have a 10,000 gallon bare steel tank, it typically takes about 1 amp to protect that tank. So in our example in this graph, I also have a 6,000 gallon tank. Well, you can kind of figure if it takes 1 amp for 10,000, it should take about 0.6 amps for a 6,000 and 0.4 amps for a 4,000 gallon bare steel tank. So in my example, I figured up that current, plus I have to have some current to protect that piping. So I figured another 0.2 amps for my piping. So looking at this chart, right away as an expert and looking at so much test data, when I see this, I automatically get in my head about how much current this system should be producing to get those structures protected. So when you do that, here we'd figure at least 2.2 amps to get this system protected. And just to let you guys know, these examples I've been giving of this impressed current system all from one site. It's all the same site. So this test data right here on this rectifier you see came from the previous slides and the following slides you'll see. This system during the last passing test had been running at 1.3 amps. If you'll see kind of in the middle to the right there, rectifier output is initially designed or last measured. The last test was 22 volts, 1.3 amps. These people replaced, there were 6 anodes in this system. These people replaced all 6 anodes at one time. When they turned the system back on, they left it set at the same tap settings, course B, fine 3, if you see there. When they did, they got a whole lot more current out of the systems because the existing anodes had been depleting over time. They got towards the end of their life. So when you installed all new anodes, you're going to get a lot more current out of that system. So, again, this is the same site. So I estimated I really needed 2.2 amps to get this site protected. They showed 5.5 amps output. That could be a problem. Also, as a regulator, when you're looking at this stuff, you want to pay attention to the current output really here. That's the important number. The rated output of the rectifier of this system, upper right corner of the graph, is 8 amps. You never want to see a rectifier run higher than its rated output. If it's rated at 8 amps, you don't want to see it running at 8.5 amps. That could be some problems. So again, as a regulator, you're really paying attention to the designed amperage output or the last measured versus what is it today. Here's the individual anode outputs of this system. When you add up all the individual anodes, you get 5.41 amps. If you saw on the previous slide, they had 5.5 amps out of the rectifier. That's what you like to see. You want to see the rectifier amperage very close to what the total individual anode amperage output is. If it's significantly different, the tester probably did something wrong. Also, in my example here, I highlighted the anodes number 4 and number 6. These are producing 1.5 amps to 1.7 amps. As I stated before, these rectifier manufacturers say their anodes can produce up to 2 amps for 20 years, but realize that the more you push that anode, the shorter its life. Also, what you have to be concerned about is when you have anodes like this, I have 6 total, but I have one of them producing 1.7 amps. I have a lot of current in one area of my tank field, and that can become a problem if you polarize the instant off numbers. The polarized potential becomes more negative than 1600 millivolts. That creates a problem we call hydrogen embrittlement. It can also literally burn coating off a tank if there is some on the tank. So something as regulators I teach, and I want you guys to know that when you're looking at an impressed current test report, you never want to see any instant off or polarized potential readings more negative than 1600. That is a bad situation, and it should not be allowed to continue under that condition. So, again, you guys are looking at these individual anodes, and you see a couple of them really high. You would expect to see readings, potential readings on tanks in the area of these high current anodes possibly being high or more negative. So here we get to our continuity test data section, and I see this every so often. I'll get a report, and this is a point-to-point continuity test that we do in an impressed current system, and it's strongly recommended that this be the type of test done on impressed current systems. The tester has written down 0 millivolts for every structure tested, and if you'll notice, structure B is listed as negative, rectifier negative all the way down. That's what you like to see. What we're concerned about is the structures to be protected must be continuous with that negative wire at the rectifier. So when you do this test, it's very simple to use one structure in your test as the negative at the rectifier, and you test everything else. Ideally, the structure is required to be protected. What's not good in this is that you see every structure is measured at 0 millivolts. That is a possibility. That can happen during a test. It's not seen that often, but it can happen. What you typically see are readings like this slide. We've flipped, and this is the one slide. It's from a different test to give you an example what you should see. The rectifier negative is listed as structure A, and they tested everything else. Well, you'll see that we have, variances in the millivolt difference between these structures. And some of those variances sometimes can be as high as 6 millivolts, 10 millivolts, and they can be continuous. But this is what you really would expect to see in a point-to-point impressed current continuity test, something like this, not the 0 millivolt reading to every structure. That can happen, but as a regulator, and I know as a corrosion expert, when I see that right away, my thought is, did they really do the continuity test, or did they just round off all the numbers so a regulator won't question them about their readings? Give you guys a little hard time there. All right, here's our local potential reading section on impressed current. So we've got all of our structures over there listed: regular tank, regular 100%, non-ethanol, premium. And you see we've got a section listed there where our reference cell was. Again, anytime a tester gives me test data, potential readings, I have to know what they were connected to when they got that reading and where that reference cell was. Otherwise, it means nothing to me. So you see we've got 2 instant off readings that are around 1500 millivolts negative. Those are of concerns. Remember, I told you that negative 1600 millivolts or more negative is a problem, and you should never have that happen. Well, this person just installed 6 new anodes, and he's running at 5.5 amps, which is way over the 2.2 amps we estimated needed to get these structures protected. So what I suspect maybe is that this test was done somewhat shortly after the repair was made, and the system was not allowed to stabilize on the polarization before he did the test. Also, I'm concerned that if the system is allowed to run longer, that these 2 test point locations I highlighted, those instant off readings may go up to negative 1600 or more negative. That is a problem and should not be allowed to happen. So as an expert, I would recommend, if I look at a test report like this, I know they just installed all the new anodes. I know my current's running much higher than it really should be, which sometimes, again, is necessary. You may have to run a system a little higher than what is estimated or calculated to get it protected. So I would recommend that this system be tested again after a period of polarization. It was also asked that I mention this. There are testers out there that are using an on potential in an Empress current system to pass or fail these systems, and that is totally unacceptable. The on reading, as I said, in the Empress current system is a totally false number. You can never use an on reading in an Empress current system to pass or fail it. There's a reason for that. There's IR drop. Some of you guys may have heard, but that's a totally false number and should never be used. Also, when taking local potential measurements or even remote readings, the reference cell should never be placed on the concrete, on asphalt, or a crack in the concrete. Again, it gives you false numbers. Here, this tester is an example, wrote, and a lot of them won't put it on their report because they know they're not supposed to do it, but this person did. He wrote, put the reference cell at a crack in the concrete. Well, that's an unacceptable test. Also, they put it at the asphalt concrete junction. There's a crack there. They showed they took a reading there. Not acceptable. You have to be in soil directly over the structure when taking local potential measurements and remote reference cell measurements. Another thing we see out there is in Empress current systems, when we're using the 100 millivolt polarization criteria, some people will use the on reading minus the instant off reading to determine if I met 100 millivolt polarization. As I stated before, the on reading should never be used for any purpose. It is a false number. So as my example here, in the first regular tank bottom drilled test hole in the center, we had 860 or 806 instant off. 806 on and 664 off. Well, that's 142 millivolts, but you're using the wrong numbers to determine the 100 millivolt polarization. You must use the instant off reading minus the ending voltage, which is defined as the static or depolarized reading. So in our example here, if the first line, you used the first numbers to determine pass or fail, you would say pass, but that's incorrect. The second line is showing the correct method, and that system, or at least that tank or pipe or whatever we're testing, would fail. So make sure you use the correct numbers. Also, Empress current system, you must take 3 local potential reading test points over each tank. Sacrificial system, there's some different standards out there. STI is 1 local and 2 remotes, but in Empress current system, 3 local test point locations over each tank. No remote readings needed whatsoever. Also, if you have some piping, you have to test at each end and in the middle if that piping is more than 100 feet in distance. In an Empress current system, all reference cell test point locations must pass either the negative 850 millivolt or the 100 millivolt polarization criteria. If one test point location in that entire system fails, then the system fails because everything is bonded together. It's one structure. So you have to pass every test point location. here's my site drawing for the example I've been using. He shows our 3 tanks, the rectifier, but the things here missing here is he's not showing where my anode junction box is, which is not critical but helpful. But the main thing is that he stated he just installed 6 new anodes at this site. He doesn't show where they are. And again, as an expert, when I'm evaluating any kind of system for any reason, it's always critical or important to know where the anodes are. Where is my current coming from? So if you have a tester or a company who just repaired a system and they installed anodes, you as regulators should show or ask or require them to show where those anodes are that they installed. And if they're numbered, if it's anode number 1 in the junction box, they should number them. Again, as an expert, it's very, very useful information when evaluating a system. That's all I got today. I could go on and on, as I said, but if any of you guys have questions, you want to ask me some other information about testing, certainly you can send me an email, and I'll see if I can help you out.
All right, fantastic. Thank you so much, Rick. And we did definitely get a few questions. I don't think we'll get to all of them today just because we definitely want to have time for Alicia here closing us out. But I do want to upload these just like last time. And the first one, so Rick, maybe just a point of clarification more than a question. I got a couple of comments related to the term ground. And so the first one actually came from someone at EPA's Office of USTs. They note that while you mentioned electrolyte earlier is a good term,
yep,
the EPA regs are specific for ground. And then sort of a related comment from someone else was, the reason a regulatory agency would indicate a structure as needing cathodic protection related to contact with soil is due to the regs relating to CP requirements to components being in contact with the ground. So I don't know if you have a follow-up comment. I know those aren't really questions, but any comment on that or clarification?
Well, certainly. Like I said, I went through this with a state recently last year. The written into their regs, stating ground, stating soil, and the issue became, flex connectors and containment sumps that routinely contain water. The tank owners were fighting to say, I don't have to protect those flexes because they're in water, they're not in soil, or they're not in contact with the ground. And that's, as a corrosion situation, totally inaccurate because water, 100% water, flex setting in water is much more corrosive potentially than setting in dry soil. So, I know those words were stated in a lot of the regs, but it really should be electrolyte, anything that's conductive. I've done corrosion work on structures that were offshore platforms. That's in water. They're not in contact with the soil, but it's extremely corrosive, salt water, and it has to be protected. So hopefully that answers some of the questions.
Great. Yeah, no, thanks for following up on that, Rick. And like I said, we got quite a few folks. I don't think we'll get to all of them. I will make sure to include all of our speakers' contact info. So I've got these tabled for now, but like I said, I do want to save some time for Alicia here. So definitely thank you so much, Rick, for that presentation. And I've got these questions either queued up for in a bit or saving for later dialogue offline in between folks who asked it and our speakers here. So thank you, you, Rick. And it is now my pleasure to introduce and hand it off to our final speaker, Alicia Meadows with Virginia Department of Environmental Quality. Alicia, take it away whenever you're ready. And hey, Alicia, I think you're still on mute there, just so you know.
Thank you, Drew.
Hello, welcome.
Good afternoon, everyone. I'm Alicia Meadows. I'm the USC Compliance Coordinator for the state of Virginia. I wanted to share with everyone something Virginia developed in the late 90s or early 2000s, and we've recently updated with the new regulatory requirements. And it's Virginia's alternative to closure for upgrading violations. In the late 90s, there was a deadline for corrosion spill and overfill. December 22nd, 1998. Many of you probably remember that date. So many tanks in the 90s were upgraded with either a liner or cathodic protection. And when we were conducting inspections, we were finding some really odd situations and faced with, from a regulatory perspective, how do we handle this? How does this person correct this issue? Because our world, as all of you know, is not black and white. There's lots of gray areas. So we created a matrix as a way to consistently handle all the different scenarios that we were encountering, or most of the scenarios, so that we can make sure that we handled the scenarios consistently and that we all agreed on the resolution. So what we came up with, we called a decision matrix. And this is kind of a snapshot view of it that shows you we had a column for scenarios. There were 18 scenarios that we had developed, the compliance options other than permanent closure, and then any comments that need to be made on that issue. We recently updated this for the new regulatory requirements. We didn't need to add any additional scenarios, but we had to change what we were originally doing. Also, this is subject to change. We're tightening up what we're allowing for corrosion protection and if we're allowing any upgrades. So even though this is our current guidance that I'm going to show you today, keep in mind that we're changing it and tightening it up in most likely in the near future. You can obtain this from our website. It is part of our compliance manual for underground storage tanks. It's actually Appendix E of that guidance, if any of you want to take a look at all the scenarios and what we did. So I'm not gonna go through all 18 scenarios. I'm just gonna show you a few just so you get the idea of what we did. So our first scenario is bare galvanized steel, UST, or piping. We don't have an alternative to close. We no longer have an alternative to closure for those. So if we encounter bare or galvanized steel, UST, or piping, we're requiring them to be permanently closed. There is one exception. If we encounter buried stainless steel flex connectors, we are still allowing them to be isolated from the soil or cathodically protected. But that's the only component that we are allowing any upgrades to, if you will. So one of the other things that we've encountered is we have a tank owner who already has a cathodically protected steel tank, and they want to add a liner to it. We will allow a liner to be added because it's more protective of the environment, because then you have internal and external corrosion. However, you can't add the liner and not maintain your cathodic protection system. Your cathodic protection system must be maintained in that case. It would still need to be tested every 3 years. If it fails a test, it would need to be repaired, or you'd have to permanently close the tank. From a regulatory standpoint, we do not require maintenance of the liner in a situation where the cathodic protection is being maintained. However, we would obviously encourage it. And then we have the reverse of that, where an owner wants to add cathodic protection to an already lined tank. Now, that's kind of an odd one because our regulation no longer allows upgrades, if you will. So because when you have two methods of cathodic protection that's more protective of the environment, we will allow it, but there's some stipulations. Number one, the internal liner has to pass the lining inspection prior to adding cathodic protection. The reason for this is we don't want we want to avoid people adding cathodic protection to liners that maybe have never been inspected. We have no idea what the inside of that tank looks like and the integrity of the tank. And if you were to add cathodic protection to an already corroded tank, that could be detrimental. You could have the opposite effect of protection, and you could actually accelerate corrosion in severe cases. So if the liner fails, it can be repaired. If it can be repaired to its original design specs and in accordance with the liner standard. If it's ineligible for repair, then cathodic protection may not be added, as well as the tank would need to be permanently closed. And then I already kind of touched on this, that if you're going to add cathodic protection to an already lined tank, you need to have an internal integrity assessment done on the tank for cathodic protection following the ASTM standard. And also you need to get a CP expert certification. So with everything that's required, we have had a few tank owners to go this route, but it's not an easy route. But we want to make sure that that old tank is sound enough for cathodic protection. So we wouldn't allow any non-invasive integrity assessment. They've got to go inside the tank in this case. Then we have someone who tells us that their tank is STIP free, but they have no proof. Now, usually we're using this because there's some kind of evidence contrary to the fact that it's STIP free. For instance, I've seen facilities submit registration forms at one point saying the tank was STIP free, and then later maybe we get one saying it's fiberglass, then we get one saying it's composite, and then they go back to STIP free. So then our question is, well, what kind of tank do you have? Do you know? In those cases, we may require the owner to physically demonstrate, meaning they would have to excavate above the tank so we can see the tank. Now, there are other types of documentation they could provide. If they have installation document, maybe some registration records, along with a sworn affidavit. It's unlikely we would accept just a sworn affidavit. There may be cases that we would, but most likely they're going to have other documentation showing us that the tank is STIP free. And hopefully we're not encountering that anymore, but when this matrix was written, we were seeing a lot of these odd situations. Now, this is one we may see more and more of as the tanks and their cathodic protection systems age. So if you have a STIP-free tank with an impressed current with an impressed current system added to it, and the impressed current fails the 100 millivolt shift test, what do you do? In Virginia, they would have to contact a CP expert to recommend a new design or recommend repairs, and any repairs or modifications to the impressed current system would need to be conducted in accordance with the NEI standard. Or, in accordance with the NEI standard, seeing the STIP-free tank threw me off. So that's all I had. I just wanted to kind of give you a glimpse of the thought of our matrix for these odd situations, especially with the new regulation addressing this. And I think Drew's probably going to open it up for questions at this point.
Yeah, absolutely, Alicia. Thank you so much. I did get kind of some follow-up questions for you here. So kind of a two-parter. And in the looking at the time, I'd rather just read this one aloud if that's okay. So the question,
Sure.
The first one, how quickly does the CP system need to be installed after lining installation?
What, in order to avoid the internal inspection?
Yeah, sorry.
We don't.
No, but go ahead.
We don't require that a cathodic protection system be installed. But I'll give you an example. If you installed a line tank, let's say in 1993, and today you want to add cathodic protection to that tank, as long as you do all the testing, everything I stated before, you could add it.
Okay.
Potentially if everything passed and the tank was found.
Great. And the second one, what does Virginia DEQ require if the cathodic protection system isn't repaired in a reasonable amount of time? For instance, 18 months has passed.
Oh, well, I don't think 18 months is a reasonable amount of time to repair a cathodic protection system. Typically, from a compliance process, we would allow the tank owner 90 days to repair it. We do have other enforcement tools to allow a longer amount of time, but 90 days is generally as long as we're going to allow without further enforcement, unless they enter into a letter of agreement. And okay. That's 6 months to a year possibly, but definitely will not exceed a year.
Okay. Great. So I got one more here. I think we'll finish with this third one. So this was a little longer, so bear with me, and I can read it again if it helps. So the question, the UL listing for flexible connectors requires installation chase piping or a containment sump, and Franklin Fueling specifies installation for their connectors meet UL requirements. Any specific reasoning for allowing steel flexes to be upgraded with CP? Want me to read that one more time?
No, I think I understand the question. Thank you, Drew. Well, Franklin Fueling is not the only manufacturer of steel flex connectors, but in Virginia we have buried flex connectors. And we will allow them to upgrade it with cathodic protection. Now, we would go back to, technically, we would go back to the UL standard that was in place at the time the system was installed. So if you installed it, let's say in the 90s, we're going back to that UL standard. And to be honest, I don't know if the older standard, I don't think the older standard required the stainless steel flex connectors to be isolated from the soil. That may be something more recent.
Okay. All right. Well, I think that's about our time. Thank you so much, Alicia, for your presentation, and thanks folks for getting those last couple questions in there. And I'm going to pull up just in a second here, because I know there were some outstanding questions really for the whole panel. All four of our speakers had questions I couldn't get to. So I do want to make sure that you can see all of our panelists' contact info as well as mine. And I do want to thank our speakers, Steve, Kevin, Rick, Alicia. Great job in preparing. A lot of fun working with you to get this